Column model.
from E section
Where is your busy laptop?
because he told he let me take it because he's giving a
And the model kind of learns from this data by going to some algorithms,
We'll keep it in
going
the
to some
middle.
learning techniques, etc. and so on.
No, not there. In the middle bench.
Now, after the model actually learns from this,
How much charges?
you kind of have a small kind amount of data called validation.
92%.
Now, most people don't actually follow this, but they're supposed to follow this. So, you
But
have
there's also a
small
charging
amount of
port
data
there.
called validation,
You can connect it
which essentially lets you test out various parameters in the model. So think of it like a practice ground where you are practicing. Let's say when you learn to drive a car, you obviously practice somewhere before actually taking it on the road. Right? So think of this validation as like your practice ground where you practice, where you drive a car. So this is basically you feed in like a small amount of data, let's say data 2. And you essentially like kind of get an idea on what exactly happens here. In the third stage is the testing stage, where you again take a separate amount of data and you apply your model on it, and you get your predictions. Now, when you deploy in the real world, this is usually the last stage, the testing. Now, this is a very surface and high-level overview of the entire process. Have you guys understood this so far? Okay. Yeah.
So the first one, data, you're inputting data inside the model.
Yeah.
Second one, during the validation, that's during the second part of the training, you again put
You put a separate amount of data. It's a very smaller amount of different data that you take. It's only to figure out if your model is doing well or not. So, for example, let's say your model isn't doing really well. Now, what you figure out that okay, maybe if I change this one small thing here, I will be able to do better. So I do it on the validation. And then let's say I reach a point where I have satisfactory level of performance on both training as well as validation. And then I can say with surety that okay, I can move on to testing. Yeah. Anything else? Also, guys, preferably I like to keep this a discussion and not a talk. So I'm going to be asking a lot of questions here and there, just to make this more interactive, because I don't want to be the only one talking here. So if this is okay with everyone, I'm just going to quickly go ahead and start. First years, mainly directed first years. You guys okay with the basics of this? These 3 steps? Okay. Okay, so we are going to start off with a classification of models called foundation models. Now, generally, foundation models are considered to be a part of advanced machine learning concepts, but I'm going to break it down into a very simple level so that all of us can understand. So, how many of you guys here can drive a car? Okay, can you stand up? Okay, anyone else? You stand up. Okay, which car do you have?
I have an i20 as well as a Kia.
Okay, let's focus on the i20 for now. Which car do you have? Okay, do you think if he lends you your car, he lends you his car, you can drive his Swift Desire?
Yeah.
Right, you can, right? Anyone else got a car? Yeah, stand. Sorry? I can't hear you, sorry. Oh, okay, fine. Sorry, I'm not too well versed with cars. Okay, okay. So you said you had an i20, right? So do you think you can drive his i20? Okay. Now, why do you guys think you can drive his car? Like, it's his car, right? Same mechanism, right? Same mechanism. Now, let's say I give you an auto rickshaw to drive. Probably some of the practice. Maybe not on the first day. Maybe on the second day. Maybe on the third day. Maybe on the 5th day. Who knows? Right. Now, similarly, okay, you guys can say. How many of you guys remember the values to these 2 things? Speed of light and acceleration due to gravity. Hopefully, everyone knows. Everyone knows, right? Okay. And last one, I'm guessing everyone knows, right? Hopefully, again. Okay. So I'm going to ask you a few more questions on that. So Planck's constant, does anyone remember? Maybe.
6.626.
Yeah. Small, same. Yeah. Again, with So again, regarding the third point as well, some of you might know, some of you might not know, but the answer is chloroplast. Okay, so do you guys see a pattern here? Don't focus on the concept, but focus on the larger thing that we're trying to get across.
The fact that if you get the fundamental unit, you can build from that.
Yes. Anything else any of you first years want to add on? Okay. So essentially what I wanted to get at from this example is if you know how to drive a car, you will probably be able to drive any kind of car that's out there. Because all cars are essentially kind of the same. Now, if I had to give you a slight modification of that, which is an auto rickshaw or let's say a tractor, etc., and so on. Now, maybe with a little bit of practice, you would be able to get to that. So, what you essentially do in the first stage is you kind of build your knowledge, or rather, you skill yourself across different things or a shared category of things. So, for example, you learn to drive a generic car, and then I say, okay, since I need to drive an auto rickshaw now, I'm going to spend a little bit more time to actually focus on driving how an auto rickshaw, focus on driving an auto rickshaw, and then get ahead with that. Similarly, when you guys started studying science, now all of us would have started with science as a singular subject, right? And then when we entered, let's say, 5th grade or whatever, we started studying these subjects separately. We started studying physics, we started studying chem and bio. And then what happened is, at one point in time, you started going deeper and deeper into physics. And currently, I think in your first year syllabus, you have quantum mechanics also as a very deeper level of physics that is there. So again, you went from having a very broad knowledge of things to a very deeper and deeper level knowledge. And same way for the bio thing, because I just have to give an example there. So this particular concept where essentially you start with a broad knowledge about multiple concepts, you start with a broad knowledge about multiple tasks, multiple domains, etc. It's called foundational learning. And the reason it's called that is because that is essentially how humans learn. That is, we start with generic knowledge, and then we start going towards more specialized knowledge. A lot of you are in computer science right now, but you guys would have studied every single subject that is out there until you got to PES, right? So that is basically the intuition behind foundational learning. That is, you learn just the way humans do. I think it's visible. Yeah. So you essentially study multiple concepts and you apply whatever you have learned to those concepts, plus a few other concepts that are out there. So the example that I gave, that is, you learn science and then you start learning deeper about each specific subject. And finally, if you're interested in physics or quantum physics, you kind of go deeper only into that particular subject. Similarly for math, math is actually one of the best examples here, where you start studying, let's say, numbers, then you study expressions, then you study operations, then you study expressions, algebra, and then you get to calculus. Now, what happens? Now, let's take a look. Now, this was like a surface level intuitive learning for people who are in second year or third year. So, essentially, what you do to build a foundational model is you take gigabytes of data that is available to you. You take every single kind of data that is there. You don't care about where the data has come from. Okay. Now, it should be usable, of course, but if you're talking about it, you don't really care what kind of data it is. And you essentially just feed it to your model. Okay? All you do is feed it to your model, and you hope it learns. Now, how it learns, we'll come to it later. But essentially, you hope, kind of feed all this data to your model, and then you see how exactly this model performs. Now, you're going to achieve two things through this. The first thing is, since you have trained it on a wide category of things, it will not be specialized enough for a singular task, which is the same as the driving example I gave you. Now, if you've never driven an auto rickshaw before, you're never going to be able to drive one. Okay, maybe you might be able to switch it on and do something, but you're not going to be driving like one of the auto rickshaw guys. Right. Now, what you can also do is, let's say you spend some time learning how to drive it, you will be able to do something called fine-tuning, which I'll come to later, which essentially you can sort of get higher performance on these singular specialized tasks, and therefore you kind of build upon what you've learned. So far, is everyone following? Everyone all good? Following? Okay. So for people who are interested in generative AI, GPT-4 is one of your examples, which is trained on a large amount of data. you essentially train it on whatever is possible, and you build a foundation model that can do pretty much everything. I mean, you guys would have played with ChatGPT, you guys would have asked it to generate poems, get your assignments done, etc. So that's the reason it can do that. But how exactly can we use these foundation models? Now, foundation models aren't meant to be used directly as is, unless, of course, you are looking at a task that does not require any kind of specific information or specialized information. You are supposed to be using them as stepping stones to actually get to your targeted task. So let's say you are working on information extraction, where you are trying to extract information from a large amount of data that you have. Now, a foundation model will be able to give you generic responses or satisfactory kind of answers to what you're looking for. But let's say you are trying to find out legal answers, or you want, or you're trying to do information extraction when it comes to medical documents. Now, in those cases, you cannot use a generic model. You need high amount of accuracy, and you want your answers to be as accurate as possible. So in those cases, you take a foundation model and you kind of train it again on whatever medical data you have, so that it learns from the foundation model and applies it to this kind of medical data that you have. So yes, so foundation models are basically this. We use something called transfer learning, where you essentially transfer this knowledge to another kind of downstream task. So essentially there are two stages here: foundation model building and transfer learning. Now, again, directed at second years and third years, foundation models are usually built using unsupervised techniques. That is, you only give it data, you don't really care about what labels are assigned to data. So that means you could train it on something like language modeling, you could train it on something like next sentence prediction, mass language modeling, causal language modeling, etc. and so on. These are various jargon for everyone, but people who know it will know it. Okay. Does anyone have any questions so far? No one has any questions? Yeah. Yeah, so I will be coming to transfer learning in the next few slides actually. But essentially, let's say you have built your foundation model. It's a massive model trained on large amounts of data. Now, transfer learning is a process by which you can adapt your model to, let's say, a smaller amount of data to, let's say, a different task that is, let's say, driving the auto rickshaw. So what you're doing is you're transferring the knowledge you have from driving a car to, driving an auto rickshaw. So this process where you use this knowledge and build upon it is called transfer learning. Any questions? No questions? Okay, moving on. Yeah, so as I mentioned, transfer learning, when you do, you kind of take the foundation model that is there and you apply it to a downstream task. A downstream task would be anything from, let's say, you take your large language model, which is GPT, and you could also train it downstream on, let's say, generating summaries or answering questions. Now, if you take a very specific example of answering questions for science, it's a very specific use case now. Now, what you do here is you have taken a large application such as the GPT, you have taken all that data, but you're now focusing its abilities on just being able to answer questions for, science. Yeah. So what a downstream task here is essentially any kind of fine-tuning task where you want the model to do really well on. You don't really care whether it was able to summarize or whether it was able to generate poetry or whether it was able to, let's say, do your assignments well. Okay. You are saying, I don't care about all that anymore. I want this model to just be able to do this. So essentially, that is how you do transfer learning, where you take all your foundation model and you kind of fit it on a smaller task that is there. So a similar thing is basically when you study for an exam, where you study a lot of concepts and you apply it only on the question that have been asked. Now, when a question is asked, you obviously apply only the concept relative to that question, right? You don't paste everything you know. So similarly, think of it in that way where, if a question is given, you answer only that question and nothing else. So same thing for here, which is a model for summarization that exists. can be fine-tuned for something such as question answering or paraphrasing, which is you take a large model and you kind of focus it on one very tiny aspect of it. Okay. So, any questions? No questions?
So are you deleting all the other extra content, or are you just
Sorry.
like, for example, you are transfer learning, you're taking the foundation model as a whole, which has a lot of data, and condensing it to the taking whatever you need, the priorities which you
You are not condensing it, as it. What you are kind of doing is you are training it on a different kind of data, and you're modifying what it has learned. So, for example, let's say, you learned that light travels in a straight line, but when you came to 12th grade, you're like, oh no, that's not the case. Light bends, right? That is what transfer learning does. So you went from learning that light travels in a straight line, but then you came to a very specific example where light can bend around objects.
Yeah.
That is an example of transfer learning where you have built upon concepts you already know to kind of specialize it for something that you did not know.
So what about the other data which is not,
Did you forget that light travels in a straight line? No, that. But there is a case where models can forget, which I'll be coming to later in the disadvantages.
I have a doubt. In the case of a model, when you are utilizing it to downstream, wouldn't certain amount of data be unrelated or unrequired? While finally downstream, wouldn't that end up being noise for the new downstream model?
Yes.
So aren't we supposed to?
That's called a domain mismatch.
Yeah.
So that usually occurs when you're not doing a smart work about it, which I'll come to about. Okay. What are the points that you both brought up? Are disadvantages or other possible pitfalls
Of transfers.
Yeah. So now that we've established what exactly a foundation model is and how it can tie into transfer learning, there are two very important stages that you need to know. The first stage, which is called the pre-training stage, and the second stage, which is called the fine-tuning stage. Okay. So the pre-training stage is basically the most expensive stage that is there, where you actually build the foundation model. So you take whatever data you have and you fit it on, the model that is there. As I said, you don't care about where the data is from. You just care about getting it into the model. And this takes a lot of time, a lot of computing power, because you are looking at gigabytes and gigabytes of data. Now, models such as GPT and all, the amount of data that have been trained on and the different kinds of data is insane. Okay, even if you go a few years ago, back to let's say BERT, or even if you go back to a little bit more about when Word2Vec came out, building these kind of models took most amount of time. That is, they took more time than your actual task. So actual task is done. The reason for this is because the better the foundation model, the better your task will be, as long as it is related. Which means that if you can build a model so well that it can cover whatever possible use cases there are, then adapting to a new task becomes, very easy. For example, as I mentioned about the speed of light thing, you already know the light travels in a straight line. Now, if you did not even know the light travels in a straight line, learning about the light can bend is a little bit difficult to comprehend. So based on that, you see that your pre-training stage is one of the most important stages that is there when it comes to building these foundation models. You need the most amount of data at this stage. You need a large amount of time, computing power, etc., and so on. Now, this is what we'll actually be covering today. That is pre-training. Actually, we'll be kind of covering a bit of both, but essentially, I'll be talking about how pre-training can lead to fine-tuning. Now, fine-tuning is, as I mentioned, it's a very task-specific thing. That is, you take a big model, you adapt it to a smaller task, and this stage takes very small amount of data. That is, you can literally go from gigabytes to MBs of data and get your job done. Now, the amount of data you need here is very task-specific. That is, you can get your job done with just 20 MB of data as well. Now, this 20 MB of data is only possible because of this stage. But if this stage does not do well, you might also look at gigabytes here. And of course, because you have lesser data, it takes lesser time and computing power. So, yeah. So, for example, let's take an example where we are trying to perform summarization of legal articles. So you would start off with a very large language model. Let's say you can start off with GPT-3 or 4, both of them work. And you need to kind of get it to only summarize legal articles. So there are two things that you need to do here. One is your task adaptation, and the other is domain adaptation. So now you're looking at only, let's say, I can't do this, but fine. So in step one, you have a language model that can pretty much do everything. But you don't want this. Right? You want it to do one thing, and you want it to do that only for one particular domain. So there are two things you need to do. So the first step is to actually learn legal stuff. And the second step is to actually learn how to summarize. Right. Logically, that is what it looks like. Right. So what you do is, in the first step, you always go from a task which can be easily adapted to the next task. So for example here, you know that this already knows data about everything. What you can easily do is you can out every single legal piece of advice or legal document, reports, etc. that are known. So what essentially happens now is you have gone from a model which knows everything out there in the world to a model which knows very well only about legal things. Yeah. So good at detecting. That technically is your transfer learning example. The foundation model is pretty much anything that is taken with large amounts of data. Now, if you declare your foundation model to be something that you train on every single read of doc that is there, it becomes a foundation step for your next. So yes, foundation models are nowadays only classified for GPT models and bot models. But essentially, any kind of parent model that does everything and then goes narrower into a smaller model becomes a foundation step. But yeah, hydrating about this again. So you have gone from a model that knows everything to a model that knows everything about legal stuff. So don't worry about what exactly it knows or doesn't know. So just know that it knows everything that is there about legal documents. So now you have done your domain adaptation, which means you have gone from everything to legal. But you still have not managed to find a way to actually do the task that you're looking to do, which is where task adaptation comes in, which essentially means that you take whatever model you have and then kind of force it or rather adapt it to a specific task you want to achieve. In this case, being summarization. Now, usually you need this and this to be similar. That is, you cannot take a model which does image classification and does try to summarize. But these are very technicalities that we're not getting into. I'm just coming into it. So essentially, yes. So there are two steps here: domain adaptation and task adaptation. Now, it is possible to cover both in a single stage, and a lot of models do that. For example, if I directly find data that is capable of summarizing legal documents, that is, I take a big legal document and I can summarize it into a small legal document, then I can directly use it. But usually people do not do that because, again, as I said, we follow a very modular approach. Where you take a model and you build on top of it, and then you build on top of it, and so on. So yeah, it is possible. People do that in some specific cases where data is available, but finding a very specific use case like this is usually very difficult. Yeah. So these are people who already know a little bit about model layers, but essentially sometimes, let's say you have a very deep neural network, then let's say you have 10 layers. Now what happens is, if you guys know, when you have a deep neural network, your essential feature learning takes place in the initial layers, and the last few layers are used for predictive tasks. So essentially what you can do is, after you pre-train it on whatever data you have, you freeze your initial layers, which essentially means the representations are frozen, they are solid, and then you fine-tune it on the remaining layers that you have. So this is also another method of doing transfer learning. That is, you focus only on training selective parts of a network. Yeah, people who do not know about this will probably find this very confusing, but don't worry too much about it. for this, you probably need a more basic introduction to machine learning. But any doubts, questions about this? Yeah.
This may seem kind of weird, but say you have a foundational model, right? Use transfer learning to maybe come up with something that only answers questions in depth about quantum physics. Now, if I went to this and I asked it something about reality TV, would the answer be connecting reality TV to what it knows about quantum, or
No.
would the answer just be
No, it
wrong?
depends on how effectively you train it, but ideally, no. I say ideally because the goal is to do well on that task. So let's say you do not train it enough, then it's still going to remember things it has knows from before.
So is the goal to make it forget all that extra information and only keep what's required?
It depends on the need. So sometimes you want it to forget. In which cases you want it to do well only on that particular task. You don't really care about where the model has come from. But in some cases you don't want it to forget. In those cases it might not suit you. Any other questions, guys? Okay, we're gonna have a quick exercise now. Yeah, sorry.
What's the image about?
Okay, so in a traditional machine learning thing, I didn't want to cover this because it was a little bit overhead, but you take whatever model you have. You should take whatever model you have and you fit it on your data for a specific task. Okay, so let's say you have a particular task here. You need to get this done. You have data for this. So you fit the model on this and then you apply it to this. Okay, it's a very straightforward approach. So in transfer learning, what you do is you have probably a model that does T1, T2, T3 for now. Okay. You already have, let's say, big M. Now what you do is you take M, you fit M on, let's say, T4, and then you get your task. So essentially it builds upon what it has done. So the reason you use this actually is because instead of starting from scratch, you need a lot of data here, which means you probably need GBs of data for your particular task. But you might not have that. Let's say you have only 20 MB. You can't get that done, right? But if you go from here, which has GBs of data, you can easily adapt this. So I just want to say about that. Yes. Yeah. So we'll be having a quick exercise now. So can you guys come up with a few more examples where there is a pre-training stage and there is a fine-tuning stage, and you guys go from one pre-training stage to a fine-tuning stage for any particular task, preferably not summarization.
You train it on some medical data, and then
Sorry?
say you train something where the foundational model is predominantly with medical data. You fine tune it with, what to look for if a person presents their history, and tell it to summarize what sort of disease they might have or what they might be at risk for having.
But you're still talking about large cases of medical data, right?
That's more niche.
Weather reports. Specific region.
Yes.
Like only morning in India. Maybe weather report. Create a general report. Not like general. Select a report. Then you should summary.
But you need two stages. You need to go from generic learning with a lot of things, and then it starts learning with small apps.
We learn the entire climate, weather, or
Not completely along that lines. Any ideas? Anyone?
Feed it the entire Wikipedia, like all the articles in Wikipedia, and then ask it to generate a summary or a question from one of the articles. So you ask it to generate, say, a question about quantum physics or a question about any small subfield.
So what would be your pre-training data and what would be your
The
fine-tuning data?
pre-training data would be the entire Wikipedia, like all the articles, and the fine-tuning data would be the specific field which you want to learn.
So
Say you
quantum physics.
Yeah, or if you wanted to specifically train it for question generation on, say, some subject, the fine-tuning data would be that subject's articles.
Just one second, please. you need to start with a lot more types of answers. You can go from one to the other, but it is best to always go from more. Some of it might be. Again, it depends on how much data matches. That's it. So the reason I picked up summarization here is because both are language model tasks, both are generative methods. But yeah, I understand. Yeah.
Even web browsers based on the same thing. They're like given a lot of data. You put a keyword to it, it searches based on that data, Python's that data. So for example,
Sorry, I didn't quite get you. Could you speak
for example, web browsers. For
Okay.
example, they have there like for example, if you check into Google, you can get a lot of data. A lot of data is available inside. You can download it, whether it's not that's not the problem. But if I say I want to search something, not let it be quantum physics or anything compared to that, it fine tunes to that data like the keyword.
Searches don't really use machine learning. Searches have a different algorithm. It's not machine learning. Anyone else? Nobody from this side. Again, see, that's the thing. Your tasks need to kind of go narrower. So you said you watch YouTube content and summarize, right? But here's the thing.
Right, everybody's YouTube feed is different.
Yeah.
What they watch. So then here, what you can see a person rate this content and what you based on what you.
I don't think so. Recommendation learning systems use this. There is really answer the questions and yeah.
Have the self-driving car.
Yeah.
Every country has to take more like 3 months for 2 years.
Then we use it to specifically set smart forest.
I think you can also use it when you have large data, say on any particular sport, you take data, historical data. Using that, you fine tune it to a particular aspect, and using that, you can use it for predictive analysis of say, a particular player or sports person. You can predict using
What kind of data are you talking about?
you have the entire data of almost every league, major league has historical data available on the players. So you can access the entire data, train it on that, and then fine tune it to any particular aspect you want, and then use it to predict or generate any guesses on what a player's future production would be.
Or can't you achieve that using the same Google model?
No, wouldn't you'd have lots of gray areas due to the changes in the eras, because in every sport there'll be differences due to periods and stuff. So if you have a large data, you have to fine tune it to a particular
I
sample.
never heard of this application, so I'm not too sure. But yeah, you guys get the idea where you're narrowing down the.
Yeah.
Or I don't get one. So you create a large code base or different things, and then you can fine tune it on a very single language and carry out something. Okay, everyone's gotten the link to move on. Okay, so this slide is mainly directed towards second years and third years. So usually when you do talk about transfer learning, no discussion is complete without these 4 kinds of transfer learning. The first is zero shot, which essentially stands for no transfer learning. That is, you take a foundation model and you expect it to do well directly on your test data. The goal of this is to essentially be satisfied with the foundation model itself and see how it performs. Next, you have one shot, which is from the name that you have one example for your test data that is there. So based on that, you see how it performs and you do well. Again, this isn't exactly going on what exactly one shot is or few shot is. Actually, there's a lot more involved to this. But just to give a small introduction, that transfer learning is also applied to these particular use cases. And few shot is basically an extension or rather a generalized case of the 0 and 1 shot, where essentially you have a few examples for your testing data in your targeted task, and you see how the foundation kind of model works. And finally, knowledge distillation. Knowledge distillation is actually the field I work in, where essentially you take a model which is already trained on something, and you take a model which you want to train, but you do not actually train it using traditional methods. That is, you find a way where essentially the model does not actually learn from data, but it learns from another model. So that is why it's called knowledge distillation, because you kind of share the knowledge from one model to another. You do not actually share it from the data. Yeah, so advantages, I think I already spoke of the advantages. That is, you require less data, and you get more performance of very specialized tasks, and also you need less computing power. So I think these are pretty much kind of what I've already covered multiple times so far. Now, talking about disadvantages, what these two guys brought up. So the first is something called catastrophic forgetting. So catastrophic forgetting, base class forgetting, base data forgetting, these are all referring to the same concept. That is essentially when you specialize it too much for a particular task, you forget what you've learned. So for example, I did not know the value of Planck's constant until I Googled, because I've forgotten about it now. So what happens is, the more you specialize in something, the more you forget whatever generic data you have learned. Now, pretty sure now you guys would have forgotten something you guys would have learned in 11th grade chemistry or something. Because you guys are getting more specialized in your knowledge. So in some cases, it is good because you are saying that your model is getting more specialized, but sometimes you do not want it to forget. So in a case where the forgetting happens too quickly, that is, your model kind of starts overfitting on the specialized task, that is when you call it catastrophic forgetting, because it happens way too quickly for you to control. And the last one is called negative transfer, which is something, sorry, I don't know your name, but you brought up.
Aryan.
Sorry,
Aryan.
Okay, Aryan brought up. So essentially what happens is, you take a foundation model, you apply it to a task, and then you see the performance actually is lower than the foundation model. So in this, what has happened is, your foundation model is not doing really well on your downstream task. It's kind of suffering a lot. And the primary reason for this is the domains do not match. That is, if you, let's say, take a model for legal articles, which is already trained on legal articles, and you try to apply it to medical data, you're not going to get good results. So in such cases, when you have there's a mismatch in the domains, then you have something called a negative transfer which takes place. Yeah.
When you say catastrophic forgetting,
Yeah.
how does the model forget what it has done? Does it copy of?
It does not copy the data. Right? It does not.
No, but there's a large volumes of data which is there present behind them.
The model does not store data. The model learns from the data. So similarly, like I would say, let's say you learn from an exam. When you sit in an exam, you don't sit with the notebooks. You only have what you learned. So what essentially happens is, let's say you start narrowing down what you're learning. Then you kind of end up at a point where you only know that little bit that you've learned, or little bit that you've recently learned, rather, and you forget whatever you have previously learned. So in that case, what happens is you start forgetting what you've initially learned, used in your foundation model steps. So in such cases, it is called forgetting of your base data. In some cases, what also happens is sometimes when you're also like computing how it performs on the original data, you see that it's quickly decreasing in performance. That is, it is going up in performance on your new data, but the performance decrease on your foundation model, on your foundation data, is very rapid. In that case, it's a catastrophic forgetting.
But how does it learn? So if it learns something, where does it?
So if you want to know about how exactly something learns, you need to get into the math, and which I'm not doing.
But I have a question. If we're talking about dominant suitability, isn't that would happen? Like, for example, if you're trying to make it more specialized in legal articles, and you ask it medical history or something like that, then isn't it pointless? Like,
That is the point. That is the point. So usually, when you do not have a match in your domains, then you will lead to a negative transfer. Okay, not will lead, but there's a high probability of you leading to that.
But isn't that expected?
It is expected, yes, but sometimes it does not automatically strike you. Because let us say it might not be as distinct as medical and legal. It could be something within medical. Okay, so you might have medical about, let's say, topic A, and you're trying to find for topic B, but you see that the domains are very different. In such cases, it might not be possible. You'll actually see an example of that when I come to MWP board, but even though you are trained on English, it does not work. So now we'll start off with some of the NLP concepts here. Okay. Okay, I probably forgot to mention this, but essentially machine learning algorithms work on numbers. So you cannot actually feed in text randomly like that. So essentially you need to find a way where you can represent whatever data you have in the form of numbers. So if you have, let's say, I think weather reports, as someone said, you are. Okay, yeah. So essentially you need to still convert that into numeric data. If you have text, which is language, what you're working with, you also need numeric data to actually work with it. So machine learning algorithms work on numbers, and one of the most important aspects in machine learning is finding a way to represent whatever real world entities such as text, images, etc. in the form of numbers. So if you're working with images, you'd probably use something called a CNN, which is a convolutional neural network. If you're working with text, there are multiple ways to actually learn these representations. I will be covering some basic, very basic representation methods, and yeah, so representation learning, or rather how representation learning is done in NLP, is actually via transfer learning, where NLP is actually one of the driving forces today behind transfer learning, and it has made transfer learning popular in other fields as well. So if you look at all modern day NLP, it's all transfer learning today. You take a look at your models for language understanding, which is BERT, it uses transfer learning. If you take a look at your language models, GPT, etc., they all use transfer learning and so on. So the reason for this is NLP requires a large amount of data to do well. And for some specific use cases that you're trying to tackle, you might not have that kind of data. But there is enough data to actually build a foundation step in your learning. And because there is an abundance of generic use case data, such as Wikipedia, such as books, stories, etc., and so on. So if you, it's like, for example, you guys learn how to read, right? Now, at that point in time, when you started learning how to read and write, you guys pretty much took whatever books were out there. You guys took children's books, etc., and so on, and you guys learned to read. Now you guys are learning, or rather reading from more scientific books, advanced books, and so on. But essentially, you started at that step. So similarly, you have a large amount of text data for generic use cases, but for specialized use cases, you don't really have that kind of data. So to tackle that, you use transfer learning here. Yeah. So the goal here is to build a basic language understanding in these models, and then you adapt it to any particular domain or any particular task that you have. Now, I covered this in the previous slide. That is, you have two steps: domain and task adaptation. So the main goal of transfer learning in NLP is to actually build better language understanding systems, or to advance NLU, natural language understanding. So you create models which can understand better, because here's the thing: if a model can understand better, it will obviously perform better. Every single breakthrough that has happened in the NLP world has come due to breakthroughs in language understanding, and not because of breakthroughs in generative models. So, for example, if you take a look, to give you an idea, the first breakthrough that happened in generating text came in 1997, where the LSTM model came out. However, there were no actual advancements that were made to language understanding. That is, there were no advancements made to actually, improve the way models could actually understand text. Because it's a very complex phenomenon. Think about it. So, understanding a language is not just about knowing how to spell a particular word. For example, if you give a word called apple, there is so much more to it. You know it's a fruit. You can relate it to other fruits. You know where exactly it lies in your head. So it's a very complex phenomenon that actually scientists also do not actually know. So, asking a machine to do this was at that point in time impossible, and at that point was considered a dream. So back in 1997, the only breakthrough that came for modeling, that is your generative text, was the LSTM. Until 2013. So this era was basically an era in NLP where nothing happened. Basically, NLP at one point was even considered like a dead field because there was no improvements going on, and models at that stage were not able to essentially, represent language to a point where you could actually improve performance. So in 2013, something very revolutionary happened, where a model called the word-to-vec came up. So the word-to-vec is essentially a very simple algorithm, which I'll be covering later. Is essentially, still considered as the breakthrough NLP step, because you're looking at almost 16 years, 16 years where nothing happened, and then suddenly some people from Google came and said, we have cracked it. So essentially, it was at that point considered so mind-blowing that people still use word-to-vec today to explain how deep learning was used in NLP. So word-to-vec automatically improved every single algorithm out there manifold times. That is, performance doubled over every single thing because language understanding improved. And this was going well. Until in 2016. Yeah. So in 2016, something came out called attention. So the attention concept is another concept that actually led to the current modern NLP boom that all of you might be aware of. So essentially, researchers came up with this idea that when humans actually read, if you have noticed that when you read something on your page or whatever you're typing, you will pay attention to one specific part of a word when you're reading. You will never read the entire sentence at once. Researchers were able to mimic that particular thing using attention. Then in 2017, the infamous transformer architecture came out, which pretty much changed the entire NLP landscape. In 2018, BERT came out, which by Google completely changed the landscape again. And pretty much everything after that has been everything because of this particular step. And this particular step, which is a transformer, isn't directed at generative, it's actually directed at language understanding. That is why in NLP research, people still say the only way to advance NLP is if you cause a breakthrough in language understanding. Any questions about this? Okay, so let's say when you're reading a book, you've been writing notes, right? So when you're reading a line, have you noticed that you always pay attention to one particular word when you're reading it? You do not always, when you're reading, you don't read the entire sentence at once. So what your brain actually does is, it has this capability that humans are kind of born with, that they can focus on parts of a sentence that actually matter. So for example, when you even hear a sentence such as the red car is parked outside, which word did you pay attention to most? Because your brain automatically learns to pay attention to these things. So researchers were trying to look for a way where they could mimic this kind of property in models. That is, models, instead of looking at the entire thing, they said, okay, I will look at the entire thing, but I'll also pay more attention to a few parts. That is where attention came into it.
Normal coding is
Okay, yes. You cannot really compare, you cannot really create a data analogy here. But yeah, so essentially this was kind of like the timeline how events progress. Any questions here? Okay, no. Anyway, so moving on. So now we have covered why exactly we need language understanding. We have covered what exactly language understanding is. But now the question is, how do I convert text to numbers? Right? Because it's text. Can you really convert to a number? Now, there were a few preliminary approaches that were taken to converting text to numbers, but all of them weren't really good. That is why NLP didn't progress. But then, starting from the word-to-vec approach, people came up with this algorithm that was essentially able to learn relationships of words with each other. That is, it was able to create something called a semantic space where every single word in your vocabulary was part of this large semantic space, and they were related with each other. So something like this. So researchers found a way where they could represent every single word, character, sentence, etc. in the form of a large graph called the semantic space, where every single point represents any kind of word, whatever you have, in any kind of n-dimensional vector. Now, I am getting a little bit into the math here because it is kind of a mathematical concept at the end of the day. So essentially, each dimension n here actually represents one hidden characteristic here. Now, any idea why I call it hidden?
It's not apparent in the data from the text. You can't really tell.
Yeah, so let's say I take the word train here and I say I represent using 5 dimensions. Do you know what each of them stand for, each dimension? There's no way. Because even if you take a look at how you have learned the word train, you know that there are properties. Do you know how many properties are there? No. So that is the same intuition here. That is, you can essentially represent any word in an n-dimensional space, and each dimension here has some kind of hidden meaning to it. Now, there is no way to find out what each means, so there is no point of even going into it. But essentially, it's a large semantic space where words that are similar will lie closer to each other, and words that are very, very different will lie far apart. You use something called cosine distance to kind of find the angle. Cosine distance is basically your cos theta, your angle between two vectors. And the thing is, the thing that actually was the breakthrough here was, one thing was of course representing in a semantic space, but the other thing here is maintaining relationships, which was never done before. Now, you can see this particular equation here, which is essentially king minus man plus woman gives queen. Now, on the surface level, it kind of makes sense, logic. But here's the thing: back then, it was not possible to get a machine to answer this, right? Because think about it, you're looking at a very complex question here to answer. Like, a machine should not be able to answer something like this. It does not make sense. But Word2Vec back in 2013 was able to establish this. In fact, when it came out, this particular example is still famous because if you read through the paper, which I highly recommend, this is one of the first examples in the paper, and first of actually countless examples given in the paper. And even now, if you start learning about word embeddings, you will be treated to that as the first example because it is considered as, it was, how like humans look at the invention of fire as a very big thing. In NLP, this was considered a very big thing, solving this particular relation equation. So it kind of blew everyone's minds that a model could be able to do this, and it improved performance everywhere. And before that, as I mentioned, there were a few primitive approaches. Some of you might know. That's called the bag of words and the TF-IDF. Bag of words essentially counts how many words are there. TF-IDF uses a weighting scheme. But these are all statistical methods. These aren't really neural methods like the Word2Vec. In preliminary neural methods, you have the Word2Vec, as I mentioned. Then the year after that, Facebook came up with FastText, or Meta, whatever you guys want to call it. So FastText was an improvement over the Word2Vec. They built upon whatever Word2Vec was, so 90% actually the same. Then Stanford came up with GloVe, which stands for Global Vectors. GloVe is also similar to Word2Vec. Basically, these two approaches build upon Word2Vec. There's not too much of a difference, but they also have their own pros and cons here. However, that was the end of your preliminary neural methods in learning representations. Modern methods actually use a technique called language modeling to learn, where essentially the way it learns representations is by actually modeling whatever text is given to it. That is, it learns relationships between words in a sentence. It also learns where sentences are located and so on. So the initial approaches here were Elmo and Unfit. Elmo stands for Embeddings from Language Model, and I've actually forgotten. Language Model Fine-Tune. Anyway, so then came the BERT architecture. BERT is, as I mentioned, came out in 2018 that completely discarded whatever was done and came up with 2 new methods for learning representations. And pretty much since 2018, we have been following what BERT does. That is, we take BERT and we improve upon it. that is why you have a lot of NLP nowadays when it comes to language understanding. It's called word-based understanding. That is, it builds upon what was learned. A lot of things are thrown around here. I do expect questions.
How are the number of characteristics, features decided while creating?
You can decide. You can fix it for yourself. You can keep it as 10 if you want. You can keep it as 768.
It wouldn't affect the model.
It does.
So it affects how effective the model turns out.
Yeah. So more dimensions, better data, better capturing of data. But at the same time, if you dilute it too much, that is, if you represent it using dimensions as 1,000, you'll probably see that only maybe 700 actually has it. Usually, you use numbers from 256 to 768. These are not like standard numbers. These are just like numbers. For example, if you train machine learning models, people use batch sizes in the size of 4, 8, 12. It's not a rule, but it's like a norm people have been using for decades. Yeah, someone else had a question? Yeah. So the transformer consists of an encoder and decoder. Your encoder takes in text, converts it into numbers. Your decoder takes the representation, that is this representation, and gives you the probability for each token. Okay. It's a very complex architecture. The transformer is not at all simple to understand. So just one second. So essentially, your transformer, the way it learns is you take only the encoder and you use some techniques to learn those representations. This one. Yeah. Again, so explain that. I need to go into the math. Yeah.
So vectors have relationships with other vectors. For example, Kingman plus
Yeah.
is equal to Queen. Or like for the same words, like for the same vectors, like Kingman, woman, there can be multiple, different kind of. So how does the differentiate between them?
So the word-to-vec approach, the bag-of-words, TF-IDF, parsers in cloud, none of these are able to take into account context. That is, if you have a word like bank, how many words do you know? How many meanings do you know? You have a river bank, you have the building bank, etc. and so on. Right? So the meaning of a word is given by its context. So approaches such as the LSTM approaches, as well as the transformer approaches, they don't look at a word to generate a representation, but they look at the words around it to generate its representation. Something that the word-to-vec did is it would look at that word and try to figure out how it fits into that sentence. What the transformers do is they look at the context around it and see how the word fits. Yeah. So a semantic space is basically, let's say you know 10 words only. In your vocabulary is 10 words. So a semantic space is basically this n-dimensional space. You can't obviously visualize it. So think about it in 3D. Okay, a 3D space where each word is a point in that space, and these points are actually vectors, right? So each word can be related with another word. So all these words, they lie in this 3-dimensional space, and they have properties, they have characteristics, they have a direction also actually, and they can actually have relationships with others. It can be 1,000 also. Yeah. You can't. Yeah. Yes, they have the same properties. They have an angle, they have a direction as well. They also have a magnitude. Exactly. You find. Sorry?
In the second picture, what are the arrows like?
So the arrow just represents, one particular vector, So, vectors have a direction, right? So similarly here, each point here is actually converted to a vector. Because that is why you have an n-dimensional. So you have a direction here. So words that actually mean similar, they actually have similar directions. So you will have probably something like this. I know it does sound complex and it sounds a little bit, out of this world that you can, convert a word to a vector that you have learned. But that's the beauty of mathematics. So if you want to learn more about how exactly this is performed, you can read through it. You can read through the paper, but you do need a lot of machine learning, like maths, to actually go. So I've said this multiple times on Discord and WhatsApp that machine learning is primarily math. So now you guys can see where the math starts coming.
Since the characteristics and features are actually not like directly the physical characteristics of the
No.
word,
These are hidden.
wouldn't similar words which have large differences in spellings and stuff actually plot quite far off? Like say
So-
you have something like king, queen, monarch, they're all quite similar.
Similar, yeah.
They might plot quite far off due to the difference in whatever how they're spelled and written, right?
No,
you are
because
spelling
spellings don't matter in what to write. So you only look at the context in which it appears.
so the characteristics are actually based on the meaning of the word.
Exactly. It looks strictly at the meaning. Any other questions? Yeah.
Each word
Yes.
every word has those characteristics. Right? Attaching every property you can give a new meaning. Will you
Yeah, I mean, if you do, see, technically, if you do king minus man, it does mean something, but can you express what it means? Some of them don't have a meaning, but some of them, if you do a computation, you see that the model can compute something.
be able to generate a meaning based on the
It is able to use these representations, and it has. So that is why you say that word embeddings actually do the language understanding process. So far, so good. Oh, sorry. Okay. So I'm going to quickly walk you through 6 approaches that are taken to learning representations. Now, the first 2 are actually what BERT uses nowadays, and BERT-based architectures build on this. And I'll be just quickly recapping what is already inside. So you guys would have all solved fill in the blanks questions, right? Very basic kind of question. And why do you guys think you can solve fill in the blanks? Any idea?
Because you're given the context of whatever the entire sentence, and you can using that you already have a base knowledge plus you're given the context, it'll be easier.
Correct. You are not looking at the blank and coming up with a word automatically. There is a thought process behind it. You are looking at the context before it. You are looking at the context after it. So that is something called masked language modeling, where essentially given a blank, you try to figure out what comes in the blank from looking at the words before it and after it. It sounds very basic, I know, but right now this one particular step it constitutes 90% of language understanding today. That is, this very basic step actually builds core functionalities of language understanding systems. There's also the reverse, that is, given a word, you can predict the context around it, but this is far more computationally expensive. They both achieve the same thing, but this is kind of harder to train, so people prefer this. The next is next sentence prediction. So, given a sentence, you will probably be able to kind of understand what is the next sentence that is following. So, I don't have an example right now, but essentially, let's say when you're reading a passage or reading a the document, etc. Now there is a kind of logical flow. Now let us say I take out one sentence randomly from that. There is a break in the flow that happens, and you immediately identify that something is missing. Now the reason you can do that is because you can sort of understand how things are supposed to flow in a context. So in that case, you use something called next sentence prediction, where essentially you learn if a sentence is followed by another sentence. So in this case, you kind of train it in this way, where you give it 2 sentences and you kind of ask it to predict whether they are kind of one after the other. So these are the 2 approaches that are used by BERT. Any questions about these 2? Okay, no questions? Okay. So Word2Vec was based on the masked language modeling objective, but it did not do exactly what this says here. So it used a modification of it where, so what BERT does is it takes the entire sentence. So let's say there are 6 words in the sentence. It will mask out it in multiple places and try to predict what goes here and what goes here. But what Word2Vec did is it took 5 words at a stretch So, okay, there are only two here, but essentially it would mask out the middle word always, and it would learn. So essentially, people found that it would learn better if you give it the entire sentence at one go, and also randomly mask. That is, you randomly mask the second word. Sometimes you mask the fourth word, and so on. So people found it did better, but essentially it builds on the same concept that you learn from context on both sides. Um, yeah, so based on both, there have been two major variations that have come out. One is the Roberta by Facebook. Roberta does not actually use sentence prediction, and it claims in the paper that it does as well without it, which it actually does, but people still do prefer bot. And then there's the distill bot, which essentially, as I mentioned before, uses something called knowledge distillation. XLM Roberta is basically Roberta, but it is trained on like 50 languages. Yeah. So these are the current approaches that are known for mass language modeling that are out there. No, not mass language, for representation learning. Like these are the core approaches for representation learning. Okay. Any questions about this slide? Well, in the next slide, I'll be giving a brief introduction or a one-slide explanation of how you can actually specialize it. I'm assuming no questions. Okay. Okay. So here's the thing. So if your data is uniform, if your data does not have any intricate details or any special things about it, these will work. Okay. These will actually cover 90% of your use cases. You don't actually need to do anything special beyond the first or even the first two. But there are a few cases in which these methods will not be enough. It needs to be modeled explicitly. So in these cases, you with special architectures to actually learn from whatever data you have. And one of them is actually my paper called Calvert here. So how many of you know what a code mix language is? How many of you know what English is? H-I-N-G-L-I-S-H. Right? Social media, Facebook, everywhere. Okay, so that's called a code mix language. The reason it's called a code mix language is because you essentially use multiple languages in the same script language that is there. So, especially for a multilingual community such as India, there's a large amount of English text that's out there. Not just English, but Hindi and other languages as well. So, the issue with this is that there is no rule on how you exactly spell words. For example, if you take any word in English, there are probably 3-4 ways to spell it. Now, all when you guys type in, I don't know, maybe in Hindi, or I'm a Bengali, so sometimes I type in Bengali on WhatsApp with my parents. Okay. So, in those cases, there are multiple ways we decide to spell words. So, what happens is when you have multiple spellings of the same word, they will end up learning different representations, and you don't want that to happen. So that's one thing to take care of. The other thing is you will not have that much amount of clean data. By clean data, I mean usable data. You cannot just go to Facebook and scrape it because obvious reasons. And what happens is normal transform-based architectures don't perform well on these tasks. In fact, we did a study and we saw that they actually do very horribly on these tasks. So there was a need to essentially come up with a new pre-training architecture which was directed only at code mix languages, and that is essentially when we came up with Calvert. So we actually came up with two Logini architectures. The one was a knowledge distillation approach, which uses KD and which is actually what we published. That is essentially what it does is it somehow takes representations that are already there from a base language such as English, and what it does is it kind of uses a teacher-student model using knowledge distillation. People who know about this, but essentially it kind of maps representations to the transcripted language. So what it does is it kind of shares whatever knowledge it has learned with the representations that are already there. Now, this was a very hacky kind of method that did really well actually, and we saw that pre-training this way was actually able to beat state of the art by 9%. But this was just one approach that we had shown. We came up with our own pre-training architecture itself, which was an end-to-end pre-training architecture. That is, you start with an empty model and you train it completely, where we used mass language modeling and NSP from BERT. So essentially, we did build a BERT-based architecture that you call, but we came up with two other tasks for it. That is what people do for learning representations nowadays is you take an existing word architecture. You know that it already uses MLM and NSP. What you start doing is you, let's say, make up another task for it. So let's say T1 and T2 are your custom tasks for your particular application. So what you do is you find data for each of these, which is usually the same, and you start creating it on this. So essentially, BERT learns from whatever existing methodologies exist, but because you're given two specific things for your own data, it also learns from this. So finally, you end up learning representations that are suited for not only generic use cases, but also for your specific tasks. So what we had done is we came up with something called an alignment-based classification loss, where again it's a little complex, but essentially we use something from the 2016 attention paper, which had come up with a way to translate using alignments. So we found a way that we could actually find an alignment with an English sentence. So for example, let's say I am going to sleep. That's the English sentence. मैं सोने जा रहा हूँ. Okay. So that's the Hindi sentence. So now there are words that you can map. For example, sona and sleep can be mapped together. So we found a way where we could learn an alignment between English and code mixed, and that was what was the main actual representation learning scheme. And the other was a similar semantic similarity that also happens here. So essentially, the third step was mainly the new normal step. So we came up with this approach that created a task agnostic model for representation learning that could be applied to any code mix task. So we showed it on two benchmark tasks that are known for code mix, and we were able to improve by 9% on them. So that is the Calvert paper that. But that's not all. So this is a specific case where you're applying to still some kind of text. But let's say the text has some kind of form, or let's say the text has more characteristics about it. For example, let's take math word problems. Now, all of us have been solving math word problems since what? 4th grade, 5th grade, something like that. Now, how do you learn representation for math word problems? Because there's a lot more to it than actually what meets the eye. Because you have things such as operands, you have things such as operators, you have things such as univariate and multivariate, you have things such as answer types, etc. So, in 2021, a paper came out called the MWP bot, which was a very groundbreaking paper for research that was directed towards solving math word problems and generating math word problems. So it utilized almost, I think, 8 different kinds of different tasks to actually learn from this. So as I said, MWPs are not like normal text. So when you come up with, let's say, different tasks, you need to think about the characteristics of the data you're modeling. So for example, when you have a math word problem, as I mentioned, you have operands, operators, and different computation techniques. So what they essentially did is they came up with all these tasks for different things. So while they were training the model, they created a task that would count from the text how many operands are there. So for example, when you have something like Sam had 10 watermelons and 10 oranges. So there are 2 operands there, right? So it would take the text, convert it into a vector, and from the vector try to find out or rather predict how many operands are there. Operand data type was essentially to predict whether the operand is a float or an integer. Answer data type is the same as operand, where whether it checks the answer is a float or an integer. Operand answer data type compatibility. So this was kind of a new one which they added, which essentially the paper says it actually worked well, but I'm not sure. So essentially, if the operands were a float, it would predict whether the answer also would be a float. Because if your operands are a float, there's a higher chance your answer also will end up to be a float, right? Because that's how numbers work. So answer magnitude is, it would find the difference in the magnitude between the operands and the answers. Operation prediction is very basic. It predicts one of the 4 operations that are present in a thing. And equation tree distance. First years might not know this, but essentially when you have an expression that is plus, minus, etc., you can represent it as postfix or prefix, right? So when you do that, you get a tree, right? So what happens is there are tree distance formulas that gives you the distance from one node to another node. So what that loss did is essentially from any particular representation and given any 2 nodes, it would predict the distance between them. So it utilized all these particular pre-training objectives to kind of learn whatever representations are out there. So there's no image for it because the paper did not have an image. But you guys can go and read the paper. That's a pretty interesting read. And because of that paper, there were significant improvements over the ordinary bot that was being used. And now MWB bot is actually currently like, what do I say? It's like become a norm when it comes to building solvers for math problems or generators for math problems. Like it has become like a staple part of the architecture. So just like how CNNs are seen as the basic things now for images, MWB bot is seen as the basic thing for math problems. So again, this was so the reason I wanted to talk about this paper is because so far we've been following only generic text. So I wanted to give an example of very specialized text where you already have a model, where you try to create a model that is for a very specific use case. That is what they did here is they took what is there, which works for any kind of text that is there, and they focused it using these particular tasks on your specialized use case. So this is one of the best examples of transfer learning that is there. Any questions about this or Calbot?
Would increasing the number of tasks really help? Like for example, you said they added operand and answer date like compatibility.
Yeah.
Did it really help, or was it really useful in?
So there's a huge table that documents the individual improvements using each training loss. You can check that. It's marginal, but yes, it is. So essentially, what we have spoken about today is you can take any existing bot model or transform architecture, and if you can come up with these particular steps, because these are actually the core part of language understanding, that is coming up with tasks for your particular use case, coming up with specific learning models, or coming up with specific use cases where what your model can learn from. If you can sort of perfect these, you kind of crack what you're trying to learn. So essentially, if you can come up with this, your model can learn from any kind of data. But coming up with this is far more difficult than actually that it sounds. So
have all these 8 methods been helpful towards getting better results, or have some of them actually turned out to be detrimental?
So the ones that give the most amount of improvements are operand counting, operation prediction, and equation tree. These other ones, that is the data types and the magnitude and this, they are not much.
They do help though.
They do help. They do help. So here's the thing: the more loss functions you have, not all will help, but most of them will help. But another question comes into the question that comes into place is it really worth it? Like if I get a 0.5 improvement, is it really big? Like you might get maybe a 10% improvement using the others and only a 0.5 using that. At that point, you might as well remove it and drastically reduce the training time.
Yeah.
Okay. Any questions this side, that side? No? Okay, so we've reached kind of the end of this. So essentially, we're going to have a quick hands-on exercise about this, where we are going to learn from structured conversation like WhatsApp, and all of us are going to discuss what could be the possible loss functions we could use to actually learn from a structured conversation like WhatsApp. Okay. So you can use any kind of data that you have on WhatsApp. So you can use messages, you can use information like contact info, like who has sent the message and the recipient of that message, and you can also use group information like the name of the group. So yeah, so this is obviously the goal, that it should learn accurate representations. So let us say you have this particular problem statement. What task do you think will actually help here? Beyond the mass language modeling and the next sentence prediction, because that's it.
mean, those are
Because when you're building language understanding systems, you are generally posed with a problem like this. That is, you are given a particular use case to learn from. You know what data you have, but now you need to find out what exactly can be used from that data.
If you look at group conversations for colleges and stuff, you can look to see if there's a certain way or certain people who bully
Certain?
certain things that tell you if a person is bullying or certain words that correspond to that. If that was the question.
You wouldn't want to pick out certain words. You wanted to learn from it. Okay, let's take it step by step. Let's say you have a message. Okay. Let's say you have a message, right? So a message has one sender and one recipient, right? So what can you do with it? Okay, so let us say you are given a problem where you need to develop a model which can learn representations from any kind of structured conversation like WhatsApp. Okay. Now, I've given an example of WhatsApp here, but you can essentially use any whatever you have. Now, you can use data that WhatsApp provides, which means you can use whatever messages are sent. You can use information from the contacts, that is, who sent the message, who has received the message. You can also use group information, which means you can use the name of the group, and you can also use participants in the group. So, try to come up with some learning objectives or tasks.
We can learn about how one person communicates with the group.
Time distributions when people are most active.
the length of the message.
So length, time, etc. So at the end of the day, you need to look at things that learn language, not metrics.
What about association? How people associate, like how people associate from one group, how people associate with each other.
You're getting close. Topics is a use case of representation. Again, things like metrics such as when something is used, etc. You cannot use that to learn. You need, raw text. So this also uses text. This also uses text. The two examples I gave before that also uses text.
Okay, what about relationships?
Yeah, you are getting close. Is there anyone else that close?
Different type of conversation based on
Okay, so let's take an example of a group. Right. So can you guys agree that people in a group have something in common? That is, you're not going to have random people in a group, right? So when you create a group, right, there is some similarity in everyone that is part of a group. Right? So can I come up with something and say that people in a group will always be related to one another in that group? Yes? Does that make sense? Now, can I also build upon that and say that usually the topic of a group is the thing that binds every single person together? Right. So usually the topic of a group, whatever the group name, subject, etc., is what actually binds people together. Right. Like that is the definition of the relationship that people have. So if I have, let's say, 3 participants. So P1, P2, and P3. Can I say that if this is the group name, all of them are similar to this? Right?
Yeah.
So one of the things that you can use is something like a membership clause, where essentially you try to learn that certain members are part of a group, and what you do is you kind of make their representation similar. So in this, for people who know, this is an unsupervised loss. That is essentially You don't have labels for it.
But how would you know, deal with two people messaging each other, not in a group?
Yeah, so in this case, two people is a specific case where it does not work out. But in a group where you do have the topic, that works out. So this is applicable only for groups. That's why I brought it. Okay, so let's focus on messages. Okay. So now you know that a message will always have a sender and a receiver. Right. Now, given a message in a group, do you think that learning a correlation between a sender and their message is useful? That is, you learn to predict, given a message, who has sent the message.
Yeah, it's useful.
Right. Similarly, if you take the reverse, that is, given a message, can you figure out who the recipient is? Now, this works for both groups as well as one-to-one. Right? So, given a message, if you learn that, okay, person A has sent the message, then automatically the context which is there in the message, or the contents of the message, and the actual person itself, you have added more relationships between that. So, it's something else you can learn from. So, you have both sender classification and you have recipient. Anything else? Someone was talking about topics, right? You are right. Think about that, how you can use it.
Would tone be important at all?
Sorry?
Would tone, like the tone of the conversation, be important?
To find out the tone of the conversation, you need to use that model itself.
How often similar topic has been practiced?
Say things such as the time distribution of a topic. It can don't really line up with, any kind of language related things. Because here, you need to find relationships between texts. So you need to find a relationship between one word and another word, or a sentence and a word, or a sentence and another sentence. So
I think from the text and the sender, you're given the details on the sender, the text, and the groups. You can figure out a person's interest, what he's into, and almost you can figure out a good amount of detail into almost each individual.
yeah, but you'll be using the same model to do it. The goal of building the model is to actually find tone, find intents, to do some sentiment analysis, etc. and so on. So right now the goal is to actually build a model capable of doing that. You're building a foundation model. Okay, so based on a topic thing that sorry?
Relate the group name to the central part of the things.
Not general topic, but what you can do is usually when you have groups, a particular participant will talk about certain set of concepts or a certain set of topics. Right. So, for example, person A might talk about topic 1 and 2, person 2 might talk about topic 3 and 4. So, it is now important to actually relate these topics or concepts that a particular person in a group talks about. So, what you can do is, since you have the messages, you already have keyword extraction algorithms in place, which can extract keywords from messages. So, if you can, what you can also do is you take whatever topics a particular person has mentioned and you sort of correlate between the person and those topics. So, similar to what was done here, essentially what you do is you take a person here now in the center and you take topic 1, topic 2, topic 3 and correlate. Essentially, you have learned from messages, you have learned from contact info, you have learned from the structure of groups, and you have also done the basic steps of language understanding, which is MLM and NLS. So, again, this might not be perfect, this might not be very accurate, but it is definitely something to start off with. So, how many of you actually took a look at the 2 notebooks that were in the GitHub repository? Okay, a few of you did. So if you take a look at the first notebook, which is the training notebook. What number? Anyway. So if you take a look at the training. Fine, yeah, no, but essentially, yeah, so essentially there are two notebooks there. Let me first show you. Okay, so there are two notebooks here. You guys can see that. Yeah. Okay, so essentially this first notebook is essentially to, train whatever, train a basic work model on your data. So now, just for example reasons, I have attached whatever, whatever data is there from the WhatsApp groups already present. So you can train it on this. You guys want, you can also export your own WhatsApp data to see how the model trains. Now this step takes 6 hours, which is also an example that building models of this size takes a lot of time and effort. So it takes 6 hours just to run one epoch, and usually you run it for multiple epochs, at least 5. So you're looking at 30 hours of training time. But I do have a model that's been trained for 2 to 3 epochs at the moment, which you can already use in this inference notebook. So one particular use case of using these representations is something called topic model. Use for now. So topic modeling is a use case where essentially you take whatever model you have and you fine tune on whatever small amounts of data you have from a larger model, and you figure out whatever topics are present. Now in this case, I have fixed the number of topics to 50 and a few other parameters which some of you might know, some of you might not know. But if I go down, so these are essentially some of our topic clusters. Now this is mainly directed towards first years who want to find out how exactly foundation models can be used. So essentially here in topic modeling, it has found a bunch of clusters which represent topics. Now if you go and over all of them, it should show one of the topics. I mean, again, it hasn't been trained on for too much time, so the performance isn't that good. But you can actually check the hierarchical clustering to get a better idea. So what this essentially shows is how topics start off from a root topic and can be broken down into n number of topics. So there are a couple of happy birthday messages that were grouped under the same topic at this level. And yeah, when someone edits a message, you can see there's a grouping that takes place at this level and so on. So essentially what has done here is it has used context and it has used these representations to actually identify topics of discussion. And at this level, you can see how topics are kind of branched from a main topic at the level. So this is a very specific use case of a particular representation learning model, but there are further use cases as well. For example, we did not focus on predicting the group in which a message was sent. So let's say you have 10 groups and you want to predict whether a message was sent in group 1, 2, or 3. That is another particular use case you can do. There are multiple other use cases you could fit these models on, but this is a small example that I wanted to sort of show you this. But yeah, that is pretty much the end of this long session that was done. So you guys pretty much a quick one slide recap on what was covered. is essentially you can use foundation models to create a large model that can tackle a lot of tasks. And using transfer learning, these models can be fine-tuned on smaller tasks that are present. Now, if you fine-tune on a smaller task, you will see greater performance on these specialized tasks that you build it on. And in NLP, transfer learning is primarily used for language understanding. Now, representation learning is primarily done using word-based architectures nowadays, where you leverage multiple pre-training tasks to kind of understand from context what is being said. So, based on the tasks, if you can choose your task correctly, you can model things such as code mix languages, macro problems, as well as what we saw, WhatsApp applications. And representations are then used for any kind of whatever task you choose, predictive task, classification tasks, etc. and so on. And that's pretty much the end for that. Yeah.
Can we have another task like what topic leads to another? So a graph where we build the dependencies between different topics.
But for that, you need to fix the topics. Right?
But like, say we have we had a few basic topics, right?
Yeah.
Using that, can we then
Using that, then yes, but you found the topics after using the model.
So can we add another layer of training? Like training
You can
once-
probably go, yeah. There is no end to fine tune. Right? You can fine tune on whatever specialized data you want at any stage. Yeah, that's it, guys. Any questions? Yeah. Okay. So essentially, there are two notebooks. So the first notebook is actually does what is on the board. That is, it changes it on whatever data you give it. There is instructions in the email how to do it for your own data. Now the second notebook is whatever it shows was the topic you want to use. That is an example where you take whatever representations you have done and you apply it to a particular
all I want that is most will so separate, right? You have like 50 types.
So the goal is,
Then it comes to 10 types.
let's say you have a large number of
It's almost like you have
now,
ASP
to find out
feature.
if you learn
You go to the file, manual,
good
inside that you have more branches. So on, you have more
So
branches. That's
other
all.
tasks would be like topic
But
model.
here's going reverse. Now you classify from top to down. So you classify down to bottom.
Final code, etc. and so on. But for these unique
That's
good
very
representations, you cannot use bad representations.
Not really.
Representation with the word
I think they taught basic little STS on how to get the basics of the data cleaning and stuff. But nothing on generating models.
Yeah,
Easy.
the model that we spoke about just now actually does. No. Innovators. The broad level.
Really used to.
It is used to learn. Yeah, innovators. Yes, you can use this one. Representation. Word stands for by relation encoder representation. You cannot use word it's used for whatever representations you learn it for. Are they used by others? So let's say you learn these representations. So you can use these representations in a neural network. You can use these representations to a linear network. So in a linear network model, you feed in numeric data. If you feed in word data, you will get significantly better results. Let's say these are foundation models which are trained on large set of use cases. So if you cover a large set of large embedding space, where data is of different types, you will not be able to get very good performance in what it is. So the goal is you are trying to build a model that does extremely well in knowledge.
Okay, so you could person as like the main component and
Topics.
a topic. So let's say we take a topic as the main component and we relate it to people who come up with the topic. Yeah. And then let's take
There are no limitations.
let's take another topic and relate it to the same people. find similarities. And based on the two topics, let's say we create a third topic which is similar to this topic. We can predict the person who can like actually come up with that topic.
There are a lot of things you can come up with when it comes to tasks. So, what the issue that we need to take care of is they should not be specialized to each person. They should not be specialized to each particular.
Is there any way of determining the usefulness of a task without training?
Without training, no. You take a bot model, you add one task, you see how it does. You remove the task, you add
So
another.
it will take a lot of time.
That's the only way. All your application studies are basically done to find out the effectiveness of each component.
So this concludes Paper Talk for guys. Hope you had a lovely time here. Hope you were able to learn a lot from Aditya. And once again, huge thanks to Aditya Bharat for coming and giving this very insightful talk. I'm sure it was very educated to you all. Thank you so much, guys.
Yeah, that's it. All of you can go into dustbin. The juice can. That's it. Thank you so much for joining us.
Thanks. I'm just coming.